All right, let's see if we can get ourselves up and running again here. Excuse me. Let's see, what was this chapter 27? Is that the... Yes, wave optics. All right. So, just to reiterate, I apologize for not being ready with the exam before spring break, but we will do it Wednesday. Instead of coming to class, just go to the Success Center at 9 a.m., take the test. Make sure that you're there on time because the test will open and let's see, how do I do the test? No, because, well, it doesn't, I guess it doesn't matter how on time you are, but if you're not there, if you have a class at like 11 or whatever, and you don't give yourself enough time, you won't have enough time. So make sure you get there. If you need to take it another time during the day, that's fine too. Because you have a class at 10, don't you? On Wednesdays? No classes tomorrow? Okay. Okay, so take it as you please, I guess. It doesn't really matter when you take it, just take it so you have time. My other classes will be meeting tomorrow. For example, we'll meet for our programming class in the afternoon. Just not this morning class. So, having said all of that, we are going to start 20th century physics. We have 1, 2, 3, 4, 5, 6, 7 chapters. How many weeks do we have left in the semester? Today, 1, 2, 3, 4, 5. I think this week is final week. So we have 5 weeks left in the semester, which means we gotta double up a couple of chapters, which shouldn't be too hard, especially with the last couple of chapters. We should probably be able to double up these 2 chapters, these nuclear physics chapters, and these 2 chapters. We should be able to double up, so that should make it work out for us. So this is where we start to get a little more, what's a good way to say it, obtuse or abstruse. Why is this thing not going to the next chapter? Special relativity. There we go. Okay. We start, and as we start the 20th century, a lot of interesting things are happening in the physics world, in the science world in general, but most of the interesting things are happening in physics and chemistry. Of course, in the late 18th century, or late 19th century, we started to understand what atoms were. For the longest time, we just didn't really know. And it wasn't really until the end of the 1800s, early 20th century, just barely 100 years ago, that they started to understand that atoms had these charged particles, and they knew that there were charged particles floating around in matter, but they didn't really understand their nature very much. But that there were negatively charged particles and positively charged particles inside of atoms, that the atoms actually had a center to them, this nucleus as we call it, and that the rest of it was empty space except for a few of these electrons floating around. I mean, if you take an atom, 1,000th of it is actually filled with stuff. 999 thousandths is empty space. And that was completely unknown. And it changed our understanding of a lot of things. And as they started to understand that, and they started to take apart atoms and understand how many, what made different kinds of matter, why was lead different than gold? They have about the same density, but lead is really common, soft, oxidizes very easily, melts very easily, but gold, very, very different. Of course, it doesn't oxidize at all. Pure gold is unoxidizable. You can think of it as. It doesn't have any problems with getting unshiny, in other words. It's a fairly soft metal, but it's much more difficult to melt than lead. It's much more rare. Lead's very common. Gold is not. So why is there these differences, and why are there similarities, and why are there differences? And they started to understand this. They started to understand the existence and the properties of protons. And they started to understand a lot of things. And as these understandings came about, another one of the understandings that came about was the understanding of light. We've learned about some of the equations that govern light, some of the things that have to do with light. And as they put all these equations together, well, not light, electricity. Let's say electricity and magnetism. As they started to understand electricity and magnetism, they put these equations together. And this one guy came along and he solved them, this guy Maxwell that we've talked about. And as he solved them, he discovered that light was that electricity and magnetism, when they work together, are a wave, and that wave has the speed of light. And so he said, well, light must be an electromagnetic wave. And so we know that now. We understand that. We've learned about that in these past few chapters. But the most interesting thing about his discovery was that the speed of light in his equations that he figured out, in all other waves, that speed can be variable. It depends on the mass of the object that's making the wave. So if you have a rope that's really massive, the wave travels differently than a rope that's not very massive. If you have material, water, for example, versus molten lead, waves travel differently in molten lead than they do in molten water because of the mass and the viscosity and other factors. So the speed of the waves depended on a lot of different things in different materials. But in the equation that Maxwell discovered, the speed of the wave was actually made up of two constants that were already known to be constant. Epsilon naught and mu naught. The permittivity of free space and the permeability of free space, which are two constants that come out in electricity and magnetism. And they don't change. And he discovered that the speed of light is related to two things that are constant. In fact, it's equal to the square root of the square root of the product of these two things. So you take the product of those two constants, take their square root, and you get the speed of light. Well, what does this mean? This means that the speed of light is constant. It doesn't change. And that has never been observed in any other wave. It had never been observed in any other wave at that point. So the speed of light doesn't change. And also what that meant is that light could travel, these kinds of waves could travel in any material. Because if it didn't change, it didn't depend on material, and it didn't matter. It turns out it does depend on material. The speed of light does change in different materials, but it doesn't change within the material. So the material, even if the material, that's not even, we'll get to that in a second. But the constant was, this amazing thing was that this speed of light was a constant. So the material is one thing, the waves and the material is one thing, but there's one other thing that it really affected, that it really had a big deal to do with, and that is relativity. Does anybody know what relativity means? Not the theory of relativity, the word relativity. Relativity has been a part of physics for all of time, for all of physics. Newton did relativity. This is not a new concept. But what does it mean? What does it mean when you say, well, things are relative? For example, I'm driving along in my truck, okay? And to me, it looks like the landscape, the road, the trees are moving past me, doesn't it? Doesn't it look like that in your truck? So relative, to me, Everything is moving. But to the person standing on the sidewalk, I'm moving, right? So what does relative mean? What does relativity mean? Yeah, it's a comparison based on a point of view. Everybody has their own point of view. We call that point of view your own, what is it called? Time frame. We call it our reference frame, not time frame, but reference frame. So everybody has their own frame of reference or reference frame where we consider ourselves to be a stationary observer and the world around us is doing what it does. Right? I'm in my car, I'm sitting still as I drive along, and everything is moving past me. Wow, that tree went by fast. Wow, this, that, the other. And you really get a feel for that when you start to come up to a stoplight and you slow down, right? As you're slowing down, maybe somebody else is taking off because you're not noticing that the light is turning red or green, right? And you get this feeling of kind of this weird motion thing going on. As one thing moves and you think it should be moving one direction, but it starts to move another direction. So you start to get some weird things going on with relativity because it is relative to your frame of reference. We don't notice it in most cases. We do usually notice it in most cases, in that case, but not in most cases. What's another case, what's another situation you've been in where you've noticed that your frame of reference is affecting your perception of things around you? Okay, why? Do you understand why that is true? And while you're drunk, you certainly won't understand why it's true. But somebody else who's watching somebody who is drunk, you will understand. When you see somebody who is drunk, are they stable physically? No, their head is moving, right? Almost always. Drunk people cannot keep their heads still. Okay? And the reason is because they have desensitized nerves in their inner ears. Those inner ear nerves have been desensitized, so they can't tell if their head is up straight. So they can't hold it up straight. Okay? So this is a problem for your frame of reference. Your head starts doing this, and what does it feel like happening? You feel like you're holding your head straight, but what's really happening is you're not. And you feel like the world is moving around you, but what's really happening is that you're moving. Right? It's your bad ability to hold your head straight. That's true of all dizziness. If you get on a roller coaster and then you get off the roller coaster, what happens on the roller coaster is the fluid in your inner ear gets all mixed up. And the fluid is the thing that helps you to feel whether you're standing upright or not. If you're standing upright, that fluid is all at the bottom of your inner ear, and your body understands that that feeling, those nerves that are being touched by that fluid, means that you're standing up straight. But when you're on a roller coaster, your head's upside down and sideways, and it mixes up that fluid in all parts of your inner ear. And you get off, and your inner ear has no idea whether you're standing up or not. And so you just you do this thing. Right? So it's a very similar situation. How about being on the roller coaster itself, or on one of those turny things that just spin and spin and spin? Do you lose your frame of reference? You start to not understand your frame of reference or not understand physics. I wish I had one of these devices, but they're difficult to make and maintain, and you have to have a place for them. But at the school where I went, they had lots of room and people to maintain this stuff, and they had a rotating room that you could do physics in. So you get inside this little room, shut the door, and they started spinning, and you do physics experiments. So what do you think would happen if you're in a room that's completely enclosed and it's spinning, but you can't really tell that it's spinning. It's spinning slow enough, you can't tell. Let's say we're sitting across the table from each other, and we're spinning, right? You and me, Matt. And I throw a ping pong ball to you. What's going to happen to that ping pong ball? It's no. Because what's happening is, let's say we're going counterclockwise like this. As I throw the ball from this point, at this point in time, while it's moving, you're rotating that way, but the ball is now free from the building. And it's going to keep going that way. And it's also going to be affected by the fact that I'm going this way a little bit, right? So it's actually going to get thrown this way a little bit. You're going to be moving that way, so the effect is that the ball's going to go this way, you're going to go this way. But what you're going to see is you're going to see a ball that goes like this. That's all you're going to see. You're going to think that I threw you an incredible curveball, right? And same with squirt guns. It'd be very difficult to squirt you with a squirt gun because the water would do that same thing. I'd have to squirt you. and maybe hit him, right? But this is the kind of physics that you deal with when you deal with relativity. Not a big deal. Let's say that I'm on the back of a truck. I mean, if you know the movement of the various things in your system, you can figure it out. It's just, we just did for this rotating room, which is difficult. But let's think about something else. Instead of rotating, let's think about just moving a straight line. So I'm a pitcher. I'm not a very good pitcher. I could probably pitch 70 miles an hour if I threw as hard as I could and warmed up and had a lot of practice so that my arm was in better shape. But I could probably pitch about 70 mile an hour fastball, I imagine. That might be dreaming, but I think I could do it. But let's imagine that I put myself on the back of a car or a truck that's going 40 miles an hour. So I'm going 40 miles an hour in this direction, and I pitch it in this direction at 70 miles an hour from my point of view. You guys are all watching on the side of the road, but how fast is the ball going according to your point of view? I'm sorry? It's going 40 miles per hour before I pitch it, right? If I'm just holding the ball in the back of the truck, it's going 40. But if I throw it 70 miles an hour compared to the back of the truck, how fast will it be going for you guys? 110, and all of a sudden I've set a world record for the fastball, right? I think the present fastball world record is 104 something. It was set last year by some crazy rookie. But anyway, I'd set a new world record for a fastball for a baseball pitch, right? And that is also relative. So you add those velocities. If I pitched it backwards, so I'm going this way 40 miles an hour, but I pitch it 70 miles an hour backwards, what would you guys see? You'd see a 30 mile an hour tops, right? It'd be 70 miles an hour relative to the truck, but it'd be 30 miles an hour relative to you guys because you'd have to subtract the 40 from the 70. And it'd be going the opposite direction as well. Right? So relativity has an effect on speeds, has an effect on motion, turning, other things if you're rotating. Relativity has a lot of effects on things. With light, it doesn't. That is what Maxwell discovered. He didn't believe it. Neither did anybody else. They tried to explain it for decades. They tried to come up with all kinds of theories why this would be. You know, light should travel faster if it's coming off of something that's moving. But light already travels so fast, you have to measure that effect, you have to have it coming off of something that's moving really fast. Now, it just so happens that we live on something that's moving pretty dang fast. The Earth is moving really fast through the solar system. And it's rotating pretty fast around on its axis. The surface of the Earth is moving pretty fast. And so these two guys came up with this experiment to test Maxwell's theory. Maxwell, you know, everybody had been, and in fact they were trying to prove it wrong, is what they were doing. They were trying to prove that Maxwell was wrong and that there was something wrong with this. So what they did is they created this experiment that's called a interferometer. And they didn't actually invent it, I don't think. But let's take a look at this. Trying to remember the guys' names here. Can't remember the names all of a sudden. Michelson and Morley, and this is their actual interferometer right here. Now let's take a look at what this looks like in a general sense. Here is an interferometer. You have a light source, and it hits this mirror that is only half reflective. That means, you know, a mirror is made by taking a flat piece of material and covering it with something, or it doesn't have to be flat, but covering something with something very shiny so the light reflects, right? But what they do is they take a piece of glass, which light normally goes straight through, and they put dots of reflective material on it on over half of the surface, so that half of the light that hits this mirror will reflect. The other half will miss the dots and go through. So you have light that goes through, that goes straight through to the right, and light that bounces upward to the other mirror. Now these two other mirrors are full reflective mirrors, and one of them can be moved. The top one in this case is moved, can be moved. So what you do is you set this up somewhere, on a non-moving environment, and you adjust these mirrors. You adjust the movement. Now, why would you want to adjust that? Because remember that light is a wave. Remember when we bounce the light through the slits, we put the laser through the little doors, and when you got two waves, they interfere with each other and they go light, dark, light, dark, light, dark. Right? That pattern is well known and well understood. And it should show up just right if the light is coherent. In other words, if the light is coming from the same source, if the two lights are coming from the same source, going through the two holes and then combining them, you should understand exactly what that pattern should look like. However, if the two lights are coming from different sources, that means the waves will be off a little bit. The peak on this wave will be slightly behind or ahead of this peak on the other wave, if they're not coming from the same source, or if they're coming from different distances, right? That's what made that light, dark, light, dark, light, dark pattern when it came different distances. So, in this device, if you go different distances down either of these arms, to the right or up, then if you're going different distances, you will see a light, dark, light, dark, light, dark interference pattern. If you're going the same exact distance, you will just see light. So this device can tell you whether or not light has gone to different distances, but it would also work for speeds. If the light was going a different speed in one direction than the other direction, then it would also give you a light, dark, interference pattern. So what Michelson and Morley were trying to do is they were trying to show that if you had this device and you adjusted it so that you had no diffraction pattern, in other words, the light going one direction was going the same speed as the light going the other direction, and then you turned this device so that one arm was going faster than the other arm. So, for example, turn it in the direction that the Earth travels around the sun, right? If you turn this device so one arm is pointing in the same direction that the Earth is traveling around the sun, and also turn it in the same direction that the Earth rotates on its axis, then you would be going a lot faster than the other arm. In fact, the other arm being perpendicular to that speed wouldn't have any effect on those speeds at all. And they wanted to show that you would get a diffraction pattern from doing this because one arm would be going faster than another. And no matter how many times they did it, no matter how careful they were never able to show a diffraction pattern. Their device was floating on top of this huge granite block it was put on this huge granite block for stability, and then it was floating on top of a pool of mercury for stability, so that vibrations wouldn't affect it, because any vibration will cause a diffraction. But, I mean, they had stable light no matter which way they rotated this thing. It didn't matter. In other words, they proved that the speed of light in air is always the same speed. It never changes. Doesn't matter if it's on a truck. So if you have a light flashlight on the back of the truck instead of a pitcher, and you shine that flashlight in the same direction the truck is going, the truck might be going half the speed of light. It doesn't matter how fast the truck's going, but the light coming off of it will always go the speed of light, whether or not it's on the ground or on the truck. So if you have a race between light that's on the back of the truck and moving, and light that's sitting on the side of the road and not moving, it'll be a tie. The lights will travel at the same speed. What does this mean? This is the thing that scientists struggled with for decades, and they could not make sense of it. And there was really only one reason that they couldn't make sense of it. And it's more philosophical than scientific. The reason that mankind could not understand this is because hundreds of thousands of years before, some caveman looked up into the sky and noticed that the sun moved during the day and invented time. And I say invented time because time is an invention of man. Time is not something that is natural. Time means nothing to nature. Why would it? What is time? If the sun going across the sky is time, isn't that just a relative observation of a caveman? It's just an observation. Is the sun really moving across the sky? Well, sure, from his point of view. From every frame of reference, if something is moving. There's no such thing as a frame of reference where something isn't moving. From the sun's frame of reference, we're moving. From our frame of reference, the sun is moving. Right? From some other star's frame of reference, both the sun and the earth are moving. But does that mean that time exists in a way that has something to do with the sun? No. Time is an invention. And we assumed that it meant something important because we are born and we live and we die. And that also is a part of time, and we have a heartbeat. And so obviously, time is something that is important. But it means nothing to nature. Time is nothing to nature. There is no such thing as time. Time is a philosophical construct of a caveman. That's all there is to it. And we could not accept that. We never could accept that time doesn't exist as we think it does. Still today, most scientists can't accept it. Walk up and down the hall in any university, in any science building in the world, except for a physics building, and ask people if time exists. And they'll say, of course it exists. You will not find anyone, except in the physics departments, that will say otherwise. And even in physics departments, you'll find dissenters. You'll find people that argue that it does and argue that it doesn't and everything else. But in reality, why would it? Why should it? It's something that was just invented by, seasons change. Many moons ago. I mean, all these things that we invented for time are just ridiculous. Even the second makes no sense. Do we know where the second comes from? It's the average heartbeat of a person under the age of 30, which is the average age of death for a caveman. Okay? Cavemen lived to be about 25 to 30 years old, and when they took their heartbeats, it was a second. I mean, that's kind of where seconds came from, is this idea that we have this pulse inside of us. It's pulsing along, right? Now, I'm not saying this to say that we're going to abolish all thoughts of time now in our calculations and in our science. We're not going to. It's become such a part of us that we can't really abandon it. We are going to use it, but we're going to have to think of it in a different way. And Einstein is the one that came along and helped us to think of it a different way. What Einstein said is that the speed of light doesn't change. Remember, what's involved with speed? What two units are involved with speed? What units are speed measured?
Magnitude.
Not magnitude. Velocity is what I'm talking about, units. When you're talking about the units for speed, how would you say how fast you can run? What would you say? How fast can you run?
Probably like meters per second.
Meters per second. Feet per second. Furlongs per fortnight. Inches per year. Whatever. Right? Distance over time. But time doesn't exist. Crap. Now what is a speed? What does speed mean now? So Einstein came along and said, you know what? Let's just assume that Maxwell is right. Let's not try to explain it away. Let's not try to figure it out. Let's just assume he's right and go from there. We will assume that the speed of light doesn't change. It is 2.99 times 10 to the 8 meters per second. Don't change it. And let's do all of our physics using that rule. One of the rules will be we will not change the speed of light. And we'll make another rule too. We'll make another rule. We're going to say that physics, according to Newton, is still okay. As long as we assume that the speed of light can't change and physics laws are okay, and we just go on without trying to resolve it in our heads, we'll just be okay if we do math, essentially. And that's what Einstein did. He did the math. He said, I'm going to now assume that Newton is correct and that the speed of light doesn't change. But I'm going to just go on from there and see what happens. And he didn't do any observations. He didn't do any experiments. He just did the math. Right? And he did the math of relativity, what we call Lorentz physics, which is the math of relativity. And he came up with a new theory of relativity, which is, of course, called the special theory of relativity. Now, why such a big introduction to that? Because it's important to understand how groundbreaking that was. That was Einstein's great achievement right there. All he said, that all there was to it is, let's just assume Maxwell's correct, and move on from there. He was the first one to accept it. He was the first one to say, I believe it. Now let's move on. But of course, all the math and everything that he did after that was also very groundbreaking, amazing, and everything else. But just the idea of accepting it was bigger than anything else. Because it took the rest of the world decades to catch up. He accepted it, and a few of his friends, his wife, girlfriend at the time, but not many people beyond that. Not many people beyond that. Certainly none of his professors or anything else. So, Einstein's first postulate. This is where he starts to put together his theory. An inertial frame of reference is a reference frame in which a body at rest remains at rest and a body in motion moves at constant speed in a straight line unless acted on by outside force. Okay, so what he's going to do is he starts setting up rules for his theory. I already gave you two of his rules. The speed of light is the speed of light is the speed of light. And Einstein's laws are still true. But this one is equally important because he's defining what we're going to call an inertial frame of reference. And this defines the parameters for his theory. The special theory of relativity only works if you move in straight lines at constant speeds. It does not work for acceleration. Acceleration is not allowed in Einstein's theory of relativity. Why did he do this? Why did he start his theory only moving in straight lines, only moving at constant speeds? Does this ring a bell in anything we've done before? Have we ever started to do something and simplified it down so that it was so simple it was ridiculous? Absolutely we have, right? We started with very simple ideas. It's exactly what Einstein did. Einstein said, I realize that this is going to be a difficult thing to swallow, a difficult thing to work with, so I'm going to start easy. We're only going to deal in a universe where things move in straight lines and constant speeds. Okay? So, if you have an inertial frame of reference, which your inertial frame of reference is usually where your observer is sitting. Not always, but usually. Usually your observer is sitting down somewhere and everything is happening around them and they consider themselves to be at rest. They're not moving and everything else is moving. But in Einstein's theory here, we're going to say that everything else that's moving has to be moving in straight lines at constant speeds. Okay, we don't care what direction they're moving in, but they can't change direction and they can't change speed. So, first thing. Now, the interesting thing about this is that inertial reference frames can be moving themselves. An inertial reference frame can move, but it has to move at a constant speed in a straight line. So, what this means, the result of this in physics is actually the first postulate. The first postulate is that the laws of physics are the same and can be stated in their simplest form in all inertial frames of reference. So as long as our frames of reference are moving in straight lines and constant speeds, Newton is cool. We're good. Physics is good, right? And it's good in every reference. It doesn't change. Physics doesn't change just because you are in a different reference frame. It's still good as long as you do the math right. The second postulate of Einstein is this one. The Michelson-Morley experiment demonstrated the speed of light is independent of motion, independent of speed, and the speed of light is constant and independent of the relative motion of the source of the light, which means it doesn't matter what reference frame you're in. It doesn't matter if you're in a moving reference frame, in a stationary reference frame, direction doesn't matter which direction you're moving. The speed of light is always 2.99 times 10 to the 8. In this one they show 3.0 times 10 to the 8 meters per second. Okay? Notice we're still using time. With physicists who actually study this stuff today, they do not measure the speed of light with meters per second. It's not measured that way. It's measured as a distance because space still exists, whereas time does not necessarily. And time, it's kind of an argumentative thing to say that time doesn't exist. As we understand it, as most human beings perceive time or think of time, it doesn't exist. But physicists have gone ahead and rolled time, and Einstein is the one who started this process, and other physicists have taken it to other levels and different stages. But what physics has done is they've made time part of space. So space has distance and volumes and all these other things. But those things, according to physicists, are intimately connected to time. There is no space without time. There's no time without space, in other words. So if you're going to talk about space, you have to talk about time. You can't just say, where's your house? My house is on 415 South Ash Street. You have to say, my house is at 415 South Ash Street at 9 o'clock this morning. That's the last time I saw it. It may have burned down since I left. It may not be there anymore. So my house time and space are connected, even in the world that we live in, even in the reference frame that we perceive. Time and space are irrevocably connected. But with light, it's even more so. So those are the two postulates. And what postulate means is, it literally means kind of a pillar. It's a pillar that the entire theory is built on, or the foundation. Yes?
I was a bit confused when you refer to the inertial frame of reference.
Okay. So, and that's easy to get confused with. All that means is that we are simplifying our physics right now. Because to this point, we've done a lot more advanced physics. We've done 2 dimensions, we've done turning, we've done rotating, we've done all this crazy stuff. We've learned a lot of physics. But now we're going way back to chapter 1. Remember in chapter 1, it was just motion in a straight line, right? We're going to start over again, and Einstein did too. We're going to only do motions in straight lines at constant speeds. We're not going to deal with acceleration. We're not going to deal with gravity. We're not going to deal with forces. Because if we do, it makes the math hard, really hard. Okay? In fact, it makes it so hard, Einstein had to invent an entirely new mathematical system. You know that quote that Einstein says, no matter what your problems are with math, I assure you mine are greater? You've seen that quote probably quoted. Mathematicians love that because they assume that it means that Einstein was bad at math. Bull crap. Einstein was better at math than any mathematician that has ever lived since. And he knew it. He knew all of the math that was known by university professors before he entered the university. He knew it all. He didn't need to go to the university to learn it. In fact, he never went to class. That's why he never graduated, because he never went to class because he was bored. He'd go to these professors and he'd look at them and think, why are you trying to teach me this crap? This is old news. People have been doing this for 100 years. Why do you need to teach me? I can learn this by reading a book or just doing the math myself. So he never went to class. He was busy inventing an entirely new mathematical system, an entire new geometry that could deal with the physics he was trying to do. He was so far beyond everybody at the time. And that's why math was harder for him, because he was having to invent it. And he was going to his friends who were mathematicians and saying, this is what we have, this is what I need, how do we bridge this gap? And he was working with people all over the place, doing amazing stuff. But all it really means when we talk about the inertial reference frame is he's trying to simplify it so he can actually do this math, because it's so hard.
It doesn't refer to inertia at all?
It does.
Separate?
It does. Inertial reference frame, the reason they call it inertial is because remember that inertia means that an object tends to keep doing what it's already doing, right? So if an object is moving, it will continue moving in a straight line until you turn it, right? So the inertia is a big part of it, actually, a huge part. If you're in a non-inertial reference frame, that means forces are acting to force you to do something that you weren't already doing. Does that make sense? So inertial reference frame just means we're going to go back to the simple days when we were just going moving in straight lines. Now Einstein will move on to non-inertial reference frames eventually. And that's his general theory of relativity, which was his great masterpiece. And we won't touch on it too much because We can't do the math. I can't do the math. I dabbled in it once in one, maybe two classes, but man, it was too far for me, too far beyond my abilities, and I decided not to go that route when I went to graduate school. I love this stuff, but I don't love it that much. So anyway, the postulates are like the pillars, and anytime you work in relativity, as you have to always, you always have to ask yourself the two questions: am I breaking the first postulate of Einstein? Am I breaking the second postulate of relativity? If you break either of those postulates with your theories or with your math or with your experiments, then you have to go back and look at what you've done, because you've obviously done something wrong. Right? Now, if you go back and figure it out and it's still breaking it, then maybe you've discovered something new. But nobody has done so to this point. 100 years later, nobody has been able to prove Einstein wrong in these theories. In fact, all they've done is prove him right. So a good example of this is just about every year or two, there's some chump or two, some group of idiots who says, oh, we've broken the speed of light. We've discovered a particle that breaks the speed of light. We've discovered a wave that travels faster than the speed of light. Well, Einstein here says that nothing travels faster than the speed of light. Nothing. The speed of light is the speed of light. It travels at a constant speed of nothing. In fact, that's actually something he said in his second theory. But anyway, the point is that one of the things that fell out is nothing travels faster than the speed of light. And the reason for that is in the math and in the physics, it's all theory, but it's been proven over and over and over again. But somebody always comes out and says, oh, we've discovered something that breaks the speed of light. And so these people that understand the theory really well go back and they look at those experiments and they look at their math and they look at their theories and they backtrack it and see if they have actually done what they think they've done. And every time they find a mistake. Every time they find an explanation for why these people thought they measured something really fast than the speed of light. And it's never worked out. Nobody has ever been able to say, we actually, and you could go online and find particles faster than the speed of light. You'll find all kinds of people claiming that they've done it, but nobody's actually, no. And of course, we would know. Why would we know if something's gone faster than the speed of light? Okay, well, what does that mean? You've got the right idea. Let's think of it a different way. So Proxima Centauri, closest planet to us, closest star to us that has planets around it. Okay. The light coming from there, or any radio signals that might come from there, takes 15 years to get here, 20 years to get here. Maybe 30 years? 30 years, I think, actually, to get here. Because the distance between here and there is so great. It's about 30 light years. So it takes light 30 years to travel from there to here. So when we look up and see Proxima Centauri, we don't see it as it is today. We see it as it was 30 years ago. Right? So, if something could travel faster than light, let's say it travels twice as fast as light, it would get here twice as fast. In other words, 15 years, right? Well, that's not a big deal, no big deal. How about if you could send me a particle in this room faster than the speed of light? So I'm watching you now, okay? And I'm watching you do your experiment over that table, and you make this particle, but it travels faster than the speed of light. But I'm watching you make it. When would it reach me? It would reach me before I saw you make it, wouldn't it? Because the light that's traveling from your experiment to my eyes as I'm watching you make it takes some time. Not much time, but some time. But the particle that you made that travels faster than the speed of light would get to my eyes twice as fast as the experiment that I'm observing. So the particle would get to me before I watched you make it. That's a causality problem. In other words, I observed something before you made it. And it actually would happen that way, according to what we understand about the physics of the universe. In other words, things would happen before, you would observe things before they happened. That make sense? No, it doesn't make any sense. That's why it doesn't ever happen, right? That's why nobody has ever been able to prove that they've traveled, that they've made something that travels faster than the speed of light. You would have to observe the effect of the experiment before you made the experiment. And people struggle with that still. They still come out and say, oh, we observed a particle going faster than the speed of light. So, yeah, when did you observe it? Did you observe it the day before you did the experiment? Because that's the only time you could ever justify saying that you observed it before, or that you created something going faster than the speed of light. You would have had to have seen it before you did it. That's the only way. And so it's the easiest way to prove people wrong. So anyway, that is actually the subject of our next experiment, simultaneity. How do we know if two things happen at the same time? Well, again, if time doesn't exist, can we know if things happen at the same time? And the answer is no. It's all relative. It's all based on your frame of reference. So here are two frames of reference. We have observer A, who is in her frame of reference on a train. Her frame of reference is an inertial frame of reference. It's moving in a straight line at a constant speed. And she's inside this train and it's completely enclosed, and she has a light. She's sitting sideways in the train. This one shows her sitting forward. Let's say she's sitting sideways and there's a light in this corner of the train, a light in this corner of the train. Those two lights are equal distances from her eyes, and they flash those two lights using the same circuitry and the same length cords so that the signals get there at the same quote-unquote time in her reference frame. And the light comes out of those lights and reaches her eyes at the same quote-unquote time in her reference frame, according to the lady. Is it true for somebody that's standing on the railroad track, on the side of the railroad tracks? Do they see those two lights at the same time? Well, the question that you have to ask yourself is distance, not time. So as the guy on the side of the railroad tracks observes this train going by, there are two lights on the outside connected to the two lights on the inside that flash at the same time relative to the lady inside. So she's seeing the lights blink at the same time. And the two lights on the outside of the train blink at the same time if you're traveling with the train. But if you're not traveling with the train, what happens? If you're standing on the side and the train's going by, what happens is that this one and this one may blink, but this one is traveling towards the observer, this one's traveling away from the observer, so in essence, this one is going to end up being closer than this one. And what's that going to do? That means that the time that this one that's closer takes to travel is going to be shorter, and the time that the other one takes to travel is going to be longer. So the person on the side of the railroad tracks is going to see them blink at different times. Because it's not about time. It's about distance. Distance is what really matters. It's about where things are, not when things happen. So simultaneity, things that happen at the same time, depend on what your frame of reference is. If they happen at the same time in your reference frame, that's great. Right? So let's go back to our Proxima Centauri, right? I'm sitting here on Earth and I observe a lunar eclipse. At the same time, I observe a flash of light coming from Proxima Centauri as the star has a bit of activity. In my reference frame, those things happened at the same time, didn't they? What about in Proxima Centauri's reference frame? No, why not? How quickly did the people at Proxima Centauri see that event that happened at Proxima Centauri? Yeah, they're going to see the eclipse delayed, right? They're going to see their event right away. We saw our eclipse almost right away. They're going to see their event right away. But there's a difference, right? Their event happened 30 years before our eclipse happened. Right? Suppose, according to their reference frame. According to our reference frame, their thing happened at the same time as our eclipse. They're not going to see our eclipse for 30 years after their eclipse. It's all about distance. It has nothing to do with time. It has everything to do with distance. Because the light has to travel the intervening distance for you to observe it. Right? And it doesn't matter if you're moving it off. Really, it's all about distance.
So, in Star Wars, they blow up the planet and we see it simultaneously. They actually, because they go, you know what that's
Sure. Yeah, Star Wars is full of these mistakes, and they don't even try to be realistic about it. So in Star Wars, they have light speed drive and they have all these other things, and when you engage the light speed drive, the stars all come at you and everything else, and it's really cool. I love Star Wars. I've always loved Star Wars, and most science geeks do. Yeah, it's full of mistakes like that because, of course, events are relative. They're relative to your distance from them. Your speed changes things because you're changing your distance to objects all the time. For example, Star Trek, and doing a comparison between Star Trek and Star Wars is actually very interesting. Star Wars never had any science people they never brought any scientists to advise them, and they didn't want to. The beginning of their movie says, in a galaxy far, far away, a long time ago, in a galaxy far, far away. What that means is that we are ignoring physics. This is some other place, It's nowhere near us, so we're going to assume that physics doesn't matter where we're going. And it's a fantasy. It's a fantasy movie. That's what it's about. Star Trek has always had science nerds on their staff to help them make it as real as possible. And that's where the warp drive idea comes from. And if you're a Star Trek geek like me, you understand that the theory behind their warp drive is that they actually warp time and space so that they can travel at very high speeds, close to the speed of light, without it affecting their inertial reference frame. Right? Without it changing what happens, without it changing what they observe or what they measure. Could it be possible? Well, sure. You have no idea how it would be possible to do that, because it's just so far beyond what we understand. But sure, maybe in a couple hundred years, which is where Star Trek takes place. Star Trek takes place 200 years after our time now. 300, if you count, really. But anyway, it takes place hundreds of years in our future where they discover these things a little bit at a time. Has an incredible backstory for the science, but they don't try to explain all the details of the science because they leave it deliberately vague because they're hoping that eventually we will figure it out. And Star Trek is brilliant at that, Doors that open by themselves. You know how they were opened in the original TV show? They had a guy sitting behind the wall with a lever. And when he saw somebody coming towards the door and it was supposed to open, he would open it. And they made this little air sound, He would open it with his lever. Well, of course, we have doors that open by themselves all the time now, but they came from that show, that TV show. That's where the inspiration came from. Okay? And that's not the only thing. Hundreds of things have come from the imagination of Star Trek people who said, in the future, we could maybe figure this out. That's a very simple example, but, the more extreme examples, like light speed travel, and all the different implications of that, certainly possible in the future. The other interesting thing is that in Star Wars, when you go the speed of light, the stars all come towards you. In Star Trek, when they go the speed of light, what happens? Do any of you watch Star Trek? The stars do come towards them, but they change color. And that is actually what really would happen. The stars would change color. They would go through what we call a shift, a light shift. So anyway, very interesting stuff. We'll learn more about that as we go. So, all right. Here they actually show a different situation where the observer observes the light hitting the person in the middle. But that's okay. It gets really interesting as you start talking about relativity and the different possibilities that can happen, and it can get really confusing as well. it's more important to remember some of the results of Einstein's theory, because the results have been proven again and again and again to be correct. And if we keep these results in our heads, then we can always kind of make proper predictions without going wayward. It's really easy to go wayward in relativity because we have no experience with this. We have no way of using our mind to think, oh, this is what would really happen, because we've never observed it. This is nothing that we have any experience with. We have no internal understanding of this. One of the things that Einstein discovered in his theory is that time dilates when you go faster and faster and faster in your frame of reference relative to when your frame of reference is going faster to a rest frame of reference. What does that mean, time dilation? Well, what does dilation mean? With your eyes, when your eyes dilate, what happens to the pupils? They expand, right? So time dilation is an expansion of time. If you think of time as seconds ticking by at a constant rate, whatever it is, right? What happens as you go faster and faster is that those seconds slow down. And if you go actually with the speed of light, they stop. And it doesn't mean that time ends for you, not like you die or anything. What it means is that your time is moving slower. So you're aging slower. If people were observing you from outside of your reference frame, you would be moving slower. Let's say you're in a spaceship going close to the speed of light, and somebody's standing by the side of the space, whatever, watching you go by, and observing you do things in your glass spaceship. Right? They would, as they're observing you, they would observe you doing things slower and slower. So you're making your breakfast. They would observe you taking 6 hours to make your breakfast if you're going close to the speed of light. It would take them so long to watch you make your breakfast because they would see you as slowing down. In your reference frame, as you're making your breakfast, it wouldn't make any difference to you. Because to you, your reference frame is just your reference frame. You're moving, but you can't feel you're moving. It's just like in your truck. You see everything going past, but in your truck, you can still make your breakfast. You can still do whatever you're doing. It doesn't affect you. So you don't even feel it. You don't even know that it's happening. But the people observing you can see it. Now, why would that be the case? Well, let's take the example that they're showing us here. Here they have a space shuttle, or let's say that it's going to be a spaceship that's moving super fast. And inside the spaceship, they're going to have a light source that's going to bounce off of a mirror and hit a receiver. And there's going to be a timer here, a little clock that's going to say how long it takes for that light to go. And for the clock that's inside the spaceship, it measures this little amount of time in the blue. It goes here, hits, and it stops the timer. And that's what they will see no matter how fast they're going, that amount of time. However, what the observer on Earth sees is he sees the light leaving the lamp, and then the spaceship moves. And the light moves with it at this angle. And then the spaceship moves some more after it hits the mirror, and the light moves with it as it bounces off the mirror and goes back to the receiver. This is the distance this light travels. This is the distance this light travels. More. So as it actually ends up traveling more according to the observer on Earth. And so the distance it travels affects the time that it takes to travel. Because light always travels at the same speed, no matter what it's on. So it takes longer for the light to travel from here to here for this observer here. So he sees the light moving a longer distance, which takes a longer time. Let's talk about a slightly different situation that is actually exactly the same as this situation. Let's instead of being the observer on the spaceship, let's on the ground watching the spaceship go by, let's be the observer on the spaceship. Okay? So now I'm on the spaceship, and I'm going to leave London. And London has the great big clock, Big Ben, ticking away, right? It's a little minute hand moment. And as I take off, I'm seeing it's noon on Big Ben as I'm leaving London, right? And I'm going along at a kind of a slow speed as I get faster and faster and faster. And I see a minute tick by, and about a minute later I see a minute tick by, but I'm not going very fast yet, right? That's fine, I haven't gone very far. I'm still, for relatively close to London, I'm maybe still in the atmosphere, but I get going faster and faster and faster. And all of a sudden I see another minute tick by, and that's great, but now I'm getting close to the speed of light. And I'm getting way far away from Big Ben. How long is it going to take that light bouncing off of Big Ben's second hand or minute hand to reach me? Well, I'm further away, so it's going to take longer to reach me. But as I get closer to the speed of light, how long is it going to take to reach me? Because the light traveling from Big Ben and my spaceship are now traveling at close to the same speeds. The light is going to have a lot harder time catching up to me. So that second hand is going to slow down, according to my frame of reference. Right?
So is this only for like acceleration, or is it just...
No, it'll work for just speeds too. Notice that I did go faster, but I didn't talk about what's happening while I was going faster. Just at a particular point in time, I'm going some speed. What's happening? Right? So, but it happens for either one. With acceleration, you get a lot more things going on. But in essence, it is the same thing.
So, since light all travels at the same speed, just to kind of solidify this, and if you're approaching the speed of light, in that example, it's not that it isn't reaching you, it's just that it's extending the image.
No, no, it's not extending the image, it's just extending the distance between you and the thing that's traveling toward you. The distance between me and the clock is expanding at a huge rate because I'm going close to the same speed as the light is. Right? I'm going the same speed as the light that's trying to reach me to tell me what time it is. If it takes the light that much more time to travel to me, the reason it takes that much more time is because there's that much more distance. It's all about distance. It has nothing to do with stretching out anything necessarily. Events will take longer, according to my frame of reference, and we do call that time dilation, which does mean time stretching. But what's really happening is the distance is increasing because I'm going so fast. Right? And it takes longer for the light to travel through that distance. And because I'm going close to the speed of light, it takes a lot of time for it to catch up to me. Right? Even if it's going to speed of light.
Extend the distance.
So,
It's extend the distance.
is there like the opposite of that, where you go towards, and it
Well,
goes quicker?
can you go at negative speed? You can go at negative velocity, but that's just speed in the other direction, right? So if we could figure out a way to go at negative speed, then yeah, that would be kind of cool, right? But what's really happening here is that eventually, at some point, if you could actually go the speed of light, you could stop time. You could be immortal. You would never die. We'll talk more about that in a second. But anyway, Einstein figured out the mathematics of this. And it's actually pretty straightforward mathematics, where you have the change in the time between the light going up and down in the spaceship is equal to 2 times the distance that it travels one way, so you go up and then back down, so that's s, divided by the speed of light, and that's in the spaceship. Outside of the spaceship, it ends up being the length of that light travels at a goes an angle, which is the velocity of the spaceship times the change in time that happens over the experiment divided by 2. And so you have to end up actually taking the average of them both. And it's actually like the Pythagorean theorem in the end. Because notice that the path is actually 2 right triangles, right? And so we actually end up doing a Pythagorean theorem kind of thing. And it turns out that we get a distance that is equal to the square root of d squared plus v delta t over 2 squared, where d is the distance that you travel in the ship, or sorry, D is the distance between the bottom and the top, the mirror and the detector here. This S is the path length, whether or not you're moving. And you go through all this algebra to solve for the change in time, because we want to know how the time is going to change. So you go through all this algebra to calculate the change in time, and this is the equation you get in the end. The change in time. So this change is actually the dilation. How much does time stretch? Okay? So the delta t, or the time dilation, is going to be equal to delta t0, which is actually the change in time in the frame of reference of the experiment. So you go back to the spaceship and you go inside the spaceship where the experiment is not moving. Right? Because inside the spaceship, the experiment is disconnected, the spaceship is sitting still. And you do the experiment in there and time the experiment, and that's your delta t0. Okay? They call that the proper time, delta t0. And you divide that by the square root of 1 minus v squared over c squared, where v is the speed of the experiment relative to the observer, or the speed of the observed relative to the observer. So in the case of the space shuttle, it's the speed of the space shuttle. The observer is watching the space shuttle go by. And then you divide that by c squared, which is the speed of light. And this thing, 1 over the square root of this thing, was given a name. It turned out to be so important in relativity. It's called the gamma factor, or relativity factor. So this is the gamma factor. Gamma equals 1 over square root 1 minus v squared over c squared. What does gamma become if you're traveling at very low speeds? If your v squared is 1,000 miles an hour, 1,000 meters per second, right? You get 1,000 squared, which is a million, right here, over a billion squared. Well, not a billion squared, 100 billion squared. What's 100 billion squared? A lot. And this number becomes almost nothing because you get a million squared over huge. Right? So this becomes 0, and you get delta t over square root of 1, which is just 1. And so your extended time, or your dynamic time, is the same as your proper time. So if you're going slow, this doesn't change anything. You have to be going at least half the speed of light. You have to be going at least 150 billion, no, it's 150 million? 150 million meters per second. Okay? For this to make any kind of difference. If you're not going 150 million meters per second, time dilation just doesn't exist. So this only matters for things that move very, very fast. It's no wonder that nobody was able to prove Einstein's theory correct for a long time. It took them a long time to prove this correct. Eventually, they did it. They created pions that are small particles that live for a very short time. For such a short time, it's very difficult to observe them. And they were frustrated. They wanted to be able to observe them for longer periods of time. They wanted them to live longer. And so they said, well, what if we created them at very high speeds? What if instead of just creating them in this lab and trying to hold them still and watch them, what if we ran them around an accelerator while we were creating them and made them going close to the speed of light? Then they should live longer because this time dilation should expand their life longer. And they were able to do it. When they created these things just sitting still, they would last a shake. They'd be gone billionth of a second. Nanoseconds or less. Super fast, femtoseconds. Super fast. They were just gone. When they created them at high speeds, they would last twice that long, 5 times that long, 10 times that long. And they could observe them. Because they were observing them as they went by in that spaceship. And they were observing them making breakfast, and it took them 5 hours instead of 5 minutes. Right? It's the same idea.
So, based off of your frame of reference, whether you're an astronaut or the observer, if the astronaut's moving at the speed of light, or past the speed of light, to both points of the frame, they move slower.
So, if
That's just it.
yeah, and like I said, this gets really confusing. trying to work it out, how we try to work it out by talking through it, is very difficult, right? The math is easier, which is why we want to get to this point. The math is actually easier, even though it's not easy, because the math won't lie to you. The math has been proven to be correct. Trying to talk through it, trying to reason through it is very difficult because we have no way of thinking about this. We'll never experience this, and we never have, right? We have no intuition for this. So it's very difficult to try to explain how you're explaining it, how we're trying to explain it. What you just said, I think, what you're asking, is does it matter if you're the observer or the observer? If you're being observed or if you're the observer? Yes, it does. The question that you might have been asking, but you're not sure if, that you may not have been sure that you're asking, is does it matter who's moving? And the question is yes and no, because that is relative, right?
It's just weird because you always think that someone moving like,
They're going away from you,
yeah,
Right.
faster.
but you're not going away from them. But in reality, you are. It really just depends on whose frame of reference you measure things from, right? And so, and again, it comes down to the fact that if time doesn't exist as we think it does, then speed does not exist as we think it does. And it has nothing to do with speed or time, it actually has to do with distances. So the distance between objects is what is important. That's what tells you what's going on. So as the distance increases between objects and then decreases between objects, it changes things. It changes perceptions. It changes the perceived simultaneity of events. It changes things for everybody. And that's really what is the big deal here. Is if we could travel close to the speed of light, it would change everything about how we perceive what was going on around us. Everything. It would change everything. And we have no intuition for that, and we can't, because we'll never get there in our lifetimes. You know, traveling close to the speed of light is only for subatomic particles. And that's it. You can't even get atoms to move that fast. We kind of can handle it. For atoms and smaller, you know.
Technically, if we were able to move at the speed of light, we turn around and no longer were the observer, would the person that we're observing stay within the same time frame, or would,
As we
once
moved away
stopped-
from them,
once we stopped, would they be in a different time frame? They would be older.
so as we're so here, this is what you're talking about is actually a paradox that Einstein talked about. Called the Einstein paradox, the twin paradox, actually. What it's called. And I'm impressed that you came up with the question because it's an important question. So you have twins born on Earth, okay? Twins born on Earth. One of them gets in a spaceship and travels close to the speed of light towards Alpha Centauri. 30 years to get there. Turns around, travels 30 years back, right? What happens? Well, according to Einstein's theory, the one that's traveling that at close to the speed of light would have their time slow down and they would age more slowly. Whereas the one that is not traveling would age at the normal pace. Right? Now, which one is moving? Which one is not? You have to think of where was the original time frame of reference. The original frame of reference was on Earth for both of them. That's where they were both born. That's the time, that's the frame of reference that they both inhabited together, right? So that one has to be the one that sits still, because that's the one they inhabited together. When he got on the spaceship, his time dilated, his time slowed down. The one that got on the spaceship, and he stayed young because his seconds were going slowly. The one at home was in the original frame of reference and got old. So he takes 60 years to go back and forth at near the speed of light, according to the guy on Earth. But according to his clock on the spaceship, it only took him minutes, maybe hours, maybe days, maybe months, but much less time.
So, like how they show in the movie Interstellar, you go to the planet.
The person on the spaceship is younger when they come back than everybody that. And it depends on where the original frame of reference starts. So if they both were born on a spaceship going the speed of light, okay? They're born on a spaceship going the speed of light, they're twins. Then the spaceship stops and drops them off on a planet and goes again at the speed of light. That's going to change things completely. Right? The one that's on the spaceship will now be the one that's going to get old. At least if I understand it. It can be very confusing because we have no intuition to this. But the math won't lie. If you do the math, and the time, the delta t0, is the time that goes by in where the experiment is happening, and the experiment is not moving relative to what's going on, to the observer, then you're good. So that's so the delta t0 is the time, is the frame of reference of the person that's moving essentially. Okay, the delta t0, that experiment is not moving relative to them because they're moving with the experiment, right? This delta t here is the observed time from somebody that's not moving. So delta t is the observed time from the observer that's not moving. The delta t0 is the time according to the person that is moving. Right? I'm sorry? No. Not so far. And nowhere near it, according to theory as well. So that's why this, okay, so I'll tell you the theory behind this. As Einstein went through his theories, one thing that he discovered is that there is a new type of inertia in relativity that's not in Newton's mechanics. In Newton's mechanics, you have mass, which is the inertia. But in the relativity mechanics, there was another thing that popped up in the math that was not mass, but it was like mass. And so what it did is it had the same effect of adding mass to objects. If you already have mass and you try to go to the speed of light, you actually gain more mass the faster you go. The closer you get to the speed of light, the more mass you gain, infinitely. So if you actually reach the speed of light, you would have infinite mass. Of course, to have infinite mass and reach the speed of light, how much force would you need if you had infinite mass? You would need infinite force to make something with infinite mass go anywhere, right? So that's not possible. So one of the things that Einstein discovered is that it's impossible for something with mass to ever reach the speed of light because it increases its mass with this new kind of inertia. Every time it tries to get a step closer to the speed of light, its mass increases and it has to have more force. And you would run out of energy in the universe trying to get something massive to go to the speed of light. Anything massive. An electron, super tiny mass. It would take an infinite amount of energy to make an electron hit the speed of light. Anything with mass is impossible according to Einstein's theory. And that was true. That was proven true. That has been measured with particles. The amount of energy that you have to put into a particle to get closer and closer to the speed of light is exactly what Einstein predicted for this increase in mass. You have to increase that force because of that increase in mass. So this is one of the genius things about Star Trek's approach to this. As Star Trek tried to make spaceships that go close to the speed of light or the speed of light or whatever else, they said they're not just increasing their thrust, increasing their force, they're warping space and time around them. That's why they call it the warp drive. It actually changes the physics around them so that they can do this without changing the mass. And that is the really interesting thing to scientists when it comes to things like Star Trek. Is something like that possible? Is it possible to understand space and time enough to warp them into a realm that we wouldn't have to increase our masses? We wouldn't increase our masses, we went faster and faster, so that we could do it. And is there a way to do that? Because if you're warping space and time together, you wouldn't necessarily change your age as you went faster and faster close to speed. you could actually have time frames that were in sync with each other, right? It doesn't make any sense according to the theory and according to the things we've discussed so far, but nothing about this makes sense. It's totally crazy. But it has been proven to be true. That's the craziest thing about it. So let's look at an example. Our first example here, an hour and a half in, right? We're going to calculate delta t, which is called the dilated time for an event with a muon. A muon being a very small subatomic particle that can be accelerated very quickly. So, and it is naturally. So cosmic rays that collide with nuclei in the upper atmosphere produce muons. The problem with these muons, they're very difficult to detect. They require an incredible amount of detecting hardware that is very difficult to make and very difficult to use, but it can be done. The muon will have a velocity of 0.950 c because the cosmic ray coming in has an incredible amount of energy. And so that energy is turned into velocity in this muon, 0.950 c, really, really fast. Definitely going to be relativistic. When something is moving close to the speed of light and is going to, that gamma factor is going to be real, we call it relativistic. So then it travels at this constant velocity and lives for 1.52 microseconds as measured in the muon's frame of reference. Okay? So in other words, the muon's frame of reference is the guy on the spaceship measuring the experiment on the spaceship. So it's just like a normal clock, normal time. It's like doing the experiment on Earth to the guy on the spaceship. So this is the life that a muon would have if it was just sitting still, 1.52 microseconds. But how long does it look to us as we observe it? That's the delta t. The 1.52 microseconds is the delta t0, delta t naught. Ours is the delta t that we're going to calculate. So we're going to calculate the stupid mouse, wake up. We're going to calculate the dilated time. So v, 0.950 c, that's the velocity of the experiment, that's the velocity of the muon. Delta t0 is the 1.52 microseconds. C, of course, is 2.99 times 10 to the 8 meters per second. And the equation is going to be delta t equals gamma delta t naught. So we need to calculate gamma, 1 over square root of 1 minus v squared over c squared. The v squared is the 0.950 c. And the c squared, we're just going to leave as c squared. So what happens is you get 0.950 c squared over c squared. The c squared is canceled. And you get 1 minus 0.0950, which ends up being 0.950 squared, which ends up being 0.8 something. So you get 1 minus 0.8, which is like 1 minus point. You end up being 0.2 or 0.1 something. And then it's 1 over that, and you get 3.20 for the answer. So that is our gamma factor. We plug it back in here, 3.20 times 1.52 microseconds, and you get a lifespan of 4.87 microseconds for that muon. So it increases it by a factor of 3.2. Here's the twin paradox. The twins born on Earth, right? One traveling relative to the other twin will be younger. The one staying where they were both born will be older. So
That's only true if we're moving at the speed of light.
no, close to the speed of light is good enough. Close to the speed of light is good enough. So if you're traveling at 0.650 c right here, they just calculated gamma for you, 1.32. 0.650 c, the gamma factor is 1.32, right? So if I travel for 50 years and I leave when I'm 20, right? I travel at 0.650 c for 50 years and come back to Earth after 50 years. That 50 years went by on my calendars on the spaceship. I'm 50 years older. I'm 70 years old when I come back, right? But the twin that I left behind is 1.32 times 50. They're 80 years old. Right? They're dead. Well, likely. They're much older. And that's only at 0.650 C, which is barely relativistic. You know, that's not even that fast compared to 0.950 C, where it's 4 times. I mean, if I left for 10 years, you'd be 40 years old, right? If I left for 5 months, you'd be 20 months old. So,
So does it put your cells in almost like hibernation?
I'm sorry?
Would it technically put your cells in almost like hibernation then?
It's not biological. Yeah. And again, this is biology, of course, would obey these laws. So yes, it's not hibernation at all. It just slows down what the biology thinks is time. You know, when we go learn in biology class, we learn about the time that a cell takes to go through mitosis or meiosis or whatever else. You know, the time that it takes to do this, the time that it takes to do that. But in biology, the time obeys physics just like anywhere else. So if the seconds get longer, then the meiosis just follows that time scale instead. You know, time means nothing. It's all about distance. And that's the thing that's so weird. Relativity throws out all of our preconceptions about time and space. Time does not exist, only space does. So, at least as we understand it. Physics, of course, has included time in here, but their definition of time, as they've written it, is actually more of a definition of space. You know, it's got velocities in it and other things. It really has to do with space. And you're right to ask these questions. These are the questions that every scientist asks and are still asking to this day. 120 years later almost, well, 110 years later, from Einstein's first paper on this, people are still asking these questions saying, nah, that can't be true. Wait a second, that doesn't make sense. But it's been proven again and again and again, and nobody's been able to prove it wrong. It complies with every experiment we've ever done concerning things traveling close to the speed of light. Now, have we ever made something living go close to the speed of light? No, not a chance. So do we really know? No. But do we have any reason to suspect it would be otherwise? No. We don't. There's no proof one way or the other except the theory. And when that is the case in science, you go with the theory until it's proven wrong. And physicists get a lot of flack for that because we have a lot more theories than most people. Our theories go far beyond our experiments, way faster than most sciences. So you won't find, for example, in biology, you're not going to find very many theories that haven't been tested with direct experiment. With physics, there are so many theories that have not, because the experiments are just so much harder to do, you know, than the biological experiments. What would happen if you crash a black hole into a blue dwarf star? You got to wait for that to happen. You're not going to do it in your lab, you know. And if you do wait for it to happen, you may never know that it happened anyway. All right, so we're going to end there. We'll get to the rest of this later. The next time, we're going to talk about length contraction. Because not only does time expand as you go faster, but this space actually shrinks. Because if time expands, then time and space are the same thing. And in velocity, time is in the denominator, and space is in the numerator. They should do opposite things. And it turns out that length contracts or space shrinks as you go faster. So we said that if you could go the speed of light, you would be immortal, right? Because your seconds would be infinitely long and you would never age. So if you go the speed of light and length contracts or space contracts, you would be everywhere at once if you could travel the speed of light. Kind of an interesting thought, being immortal and omnipresent.
Spread over the universe like butter?
No. The universe would be contracted to the universe would be contracted to a point concentrated on you. Just the exact opposite. There's not enough butter for the numbers.
Not that,
All right. I love butter, but there's not enough butter. Not enough cows. All right, guys. We're not going to meet tomorrow. I will have the test available in the Success Center for you tomorrow for all the optics chapters and electromagnetism and optics. And we'll get some homework up for this stuff. This is the time in the class where the class becomes, I mean, we've already gotten to the point where the class is a little bit easier because optics wasn't all that hard for most of it, but this is the part where it just kind of gets ridiculously easy. Sorry about that. For the next 6 weeks, we'll have very little to really do that. There's just not that much. And,
like in the way of math.
yeah, there's just not math. Problem solving in math, there's just not. It's either the math is kind of easy for the things that we can do, or the things are so hard that we're just not going to do anything at all. We're just going to talk about it and do some cool, fun experiments. And just because we're talking about things that are so far beyond the scope of this class, we're just not going to do much problem work. So, welcome to your vacation.
I like it.
All right, so we'll see you guys Thursday. Have a good one.